In this section, we are going to learn about measures of dispersion. We know that mean, median, mode are the measures of central tendency. Some of the measures of dispersion are range, standard deviation, variance. Measures of dispersion are otherwise called measures of variability. Let us consider the scores of student A in 10 different tests out of 100. And for student B, the scores are Now we will calculate the mean for the student A. So the total score is 530 and 10 tests are there. So divided by 10, the mean marks obtained by student A is 53. Let us calculate for student B. Here also the total is 530 and 10 tests are there. So divided by 10, the mean for student B is also 53. Let us plot these scores on the number line for student A and for student B. Now let us plot the scores of student B. We can see that the dots corresponding to the student B are close to each other and clustering around the mean 53, while those corresponding to student A are scattered or more spread out. So the measure of central tendency mean alone is not sufficient to give complete information about the data. Variability is another factor which is required to be studied. That's why we need measures of dispersion. The first one is range. Range of the data is maximum value minus the minimum value. Let us calculate the range for student A. The maximum value scored by student A is 100 and the minimum value is 0. Therefore, the range is 100. Now, for student B, the maximum score is 60 and the minimum score is 46 and the difference is 14. So, we can see that student B is more consistent than student A. For example, consider that a student got scores between 10 and 40. So, the range for this particular student will be 30. And another student got marks between 70 and 100, say. Range for this particular student is also 30. By looking at the range, we cannot make out who has performed well and who is more consistent and who is not. And range is a more unstable measure of dispersion. We need a more useful and more stable measure of dispersion, which is the standard deviation. Let us consider these 9 normally distributed scores, and mean for this data is the total 540 divided by 9 scores are there, 60. Now let us calculate how much each observation is deviating from the mean 60. 50 minus 60 is negative 10. 55 minus 60 is negative 5. Here also negative 5. 60 minus 60 is 0. No deviations. 65 minus 60 is positive 5, and here positive 10. Now if I add up all these deviations, the total comes to 0. That doesn't mean that the observations are not deviating from the mean. The problem arises because some of the deviations are positive and some of the deviations are negative. For a normally distributed data, the sum of the deviations will be 0. To avoid this problem, we will square all deviations to make the deviations positive. Negative 10 square becomes 100. Here 25, 0 square, 0 square, 0 square. 5 square is 25 and 100. We will add up all these squares of the deviations, which is 300. Now let us see how to calculate the standard deviation. Standard deviation of the sample is denoted by the letter S, and standard deviation of the population is denoted by the letter sigma. This symbol is also sigma, but that stands for summation. So we use this sigma to denote the standard deviation of the population. So standard deviation for this sample is, we will add all the squares of the deviations from the mean and divide by n minus 1. Since we have squared the deviations, we will take square root. This is the formula to calculate the standard deviation of the sample. Whereas the formula to calculate the standard deviation of the population is sigma x minus mu is the mean of the population whole square divided by n, and we take square root. Here we divide by the number of observations, whereas here we divide by n minus 1, number of observations minus 1, to reduce the error in the calculation of standard deviation of the sample. Variance is another measure of dispersion, that is nothing but the square of the standard deviation. Variance of the sample is denoted by S square and variance of the population is denoted by sigma square. So S for this particular data is root of 300 divided by 9 minus 1, 8, which is 6.12. Let me change the data now by including two more observations. Let us include two observations, 20 and 100, in the table. So the corresponding deviations are 20 minus 60, negative 40, and here 100 minus 60 is positive 40, and their squares are 1600. Now the last column's total becomes 3500. Let us calculate the standard deviation for the new data, which will be root of 3500 upon 8, and this value is 20.9, because in this new data the values are scattered, the deviations are more. The lowest value is 20 and the highest value is 100, whereas in the previous data the lowest was 50 and the highest was 70. So for more scattered data, standard deviation will be more, and for less scattered data, that is if the data is clustered around the mean, the standard deviation will be less. Therefore, if standard deviation is more, that means the values are scattered. If the standard deviation is less, that means the values are clustered around the mean. So if the standard deviation is less, the data is more consistent. In USMLE Step 1 exam, you will not be asked to calculate the standard deviation and variance, but you need to understand how they relate to the normal curve. Let us consider another example. If we need to decide a better medication for some disease between two different drugs, drug A and drug B, say. So the satisfactory level of the patients are taken in percentages. Let the mean satisfactory level for drug A be 70 and mean satisfactory level for drug B is also 70, say. If we take the satisfactory level along x-axis and the frequency along y-axis, let this be the normal curve for drug A. Mean satisfactory level for drug A is 70. Let this be the normal curve for drug B, and mean satisfactory level for drug B is also 70. So the measure of central tendency for both the drugs are the same, but let us check the measure of dispersion, that is measure of variability. Here range for this drug is 20, 80 minus 60, whereas range for drug A is 100 minus 40, 60. So the satisfactory level for drug A is more dispersed, whereas for drug B, the measure of variation is lesser. That means for drug B, the people have the satisfactory level between 60 and 80, whereas for drug A, the satisfactory level is between 40 and 100. Even though their means are same, the measure of dispersion is different. drug A is more variable, whereas drug B is more consistent. Therefore, drug B is better than drug A. Between the satisfactory level 60% to 80%, that is in this range, everyone benefits a good amount. And between the satisfactory level of 80% to 100%, some of them have benefited greatly. And between the satisfactory level of 40% to 60%, no benefit. Drug B is better than drug A, though they have the same mean. The dispersion of drug A is more, and for drug B it is less. In the second figure also, both the curves have the same mean and different standard deviation, but their frequencies are different. Frequency of the mean are different. For example, 70 is the mean, say 50 patients have given 70% satisfactory level, whereas for drug A the mean is 70%, but the number of patients are less, maybe 40 patients. In the second figure also, drug B is better than drug A. In these two figures, the curves are having the same mean but different standard deviations. Now see the third figure. Here the means are different. Let mean satisfactory level of drug A be x1 bar and mean satisfactory level for drug B be x2 bar. Measure of dispersion for both the curves are same, but the satisfactory level for drug B is higher in this case because it is towards the right side of the x-axis, so the values will be more. So in this figure also, drug B is better than drug A. In this third figure, means are different and standard deviations are same. Now let us see what is a confidence interval. It is impossible to study every single person in a population. So we take a sample from the population and we calculate mean x bar of the sample, and the standard deviation of the sample is denoted by the letter S. From this sample mean x bar, the estimated range for the population mean can be calculated, which is called the confidence interval. Therefore, a confidence interval is simply a way to measure how well the sample represents the population. And we can calculate the confidence interval for any confidence level we like, but the most commonly used value is 95% confidence level. Therefore, the confidence interval gives the upper and the lower values that we can be 95% confident that the mean of the population lies between these two values. Let us consider this normal curve. Let this be the sample mean x bar, and we know that mu is the population mean and sigma is the standard deviation of the population and S is the standard deviation of the sample. This is 1 standard deviation, 2 standard deviation, 3 standard deviation, and on the left side of x bar it will be minus 1 standard deviation, minus 2 sigma, minus 3 sigma. 68% of the data will be within 1 standard deviation from the mean, that is plus 1 standard deviation, minus 1 standard deviation. 68% of the data will be within x bar plus or minus 1 standard deviation. 95% of the data will be within the limits x bar plus or minus 2 sigma. And 99.7% of the data will fall under x bar plus or minus 3 sigma. So 34% of the data will be between x bar plus 1 sigma. 34% of the data will be on the right side of x bar within 1 standard deviation level, and 34% of the data will be below x bar in 1 standard deviation level. 47.5% of the data will be above x bar within 2 standard deviation, and 47.5% of the data will be below x bar within 2 standard deviation. So, between 1 sigma and 2 sigma, 13.5% of the data will fall. Similarly, in this range, we will have 13.5% of the data. So, if we say 95% confidence interval, the remaining is 5%. So, 2.5% of the data will be above 2 sigma and 2.5% of the data will be below minus 2 sigma. We will split this 2.5 approximately as 2.4 and 0.15. So, 2.4% of the data will be between 2 sigma and 3 sigma, and 0.15 data will be above 3 sigma. Similarly, 2.4% of the data is between minus 3 sigma and minus 2 sigma, and 0.15% of the data will be below minus 3 sigma level. 0.15 plus 0.15 is 0.3. So, the remaining 99.7%. Now, let us see about z-scores. Z-score gives us an idea of how far from the mean a data point is. For example, so we can calculate the z-score of a data point from the sample mean as x minus x bar divided by s. Whereas, if we use mu and sigma for the population, then z-score of a data point will be x minus mu upon sigma. So, z is a measure of how many standard deviation below or above the population mean a data point x is. So, these are the formulae to calculate the z-score if we know the sample mean and the sample standard deviation, and this is the formula to calculate the z-score of a data point when population mean and population standard deviations are known. So, this is a z-score of a sample point x. Given the confidence level, we know the corresponding z-scores. Z-score shows how far a single data point is from the mean. Lower z-score means closer to x bar, higher z-score means more far away from x bar. Positive z-score means to the right of the mean or greater than the mean, while negative z-score means lower or smaller than the mean. We can calculate the z-score of the sample mean with respect to the population mean. That will be x bar minus mu divided by sigma over root n, where x bar is the sample mean, mu is the mean of the population, and sigma is the standard deviation of the population, and n is the sample size. In the previous formula, we use one data point x, therefore n is equal to 1. That is why we do not have n in that formula. This z-score tells us how many standard errors are there between the sample mean x bar and the population mean mu, where the sigma by root n is called the standard error of mean, which is SEM. The formula is sigma by root n, or it can be taken as S by root n. If sample size is very large, sigma or S will be very small, therefore standard error of mean will be minimized. Now, let us see when to calculate the t-score. So, t-score will be calculated when the standard deviation of the population sigma is unknown and when the sample size n is less than 30. Then t-score formula is x bar minus mu divided by s by root n. In this figure, the orange curve represents z distribution curve and the blue curve represents t distribution curve. T distribution curve looks similar to the normal curve. The center will be at 0, that is the mean, and has a basic bell shape, but it is shorter or flatter around the center than z distribution curve because the sample size is less than 30. and its standard deviation is proportionally larger compared to the z. That's why we see the fatter tails on each side of the t-distribution curve. Now let us see how to calculate the confidence interval given the z-score. Let us see some of the standard levels of confidence and their corresponding z-scores. For 68%, the z-score is 1, that is 1 standard deviation. And for the confidence level of 95%, the z-score is 1.96, approximately 2 we can say, 2 standard deviation. And for the confidence level of 99.7%, the z-score will be 3. So to calculate the confidence interval, the formula is x bar plus or minus the required z-score times s by root n, where x bar is the sample mean and s is the sample standard deviation. Or if population mean and standard deviation are known, we can use them in the calculation. So if n is very large, we know that standard error of mean will be very small. Therefore, the confidence interval will be narrower. Smaller confidence interval it will be. And the standard error of mean is always less than the standard deviation sigma. Because standard error of mean is sigma by root n, it will be lesser than sigma. The confidence level and the confidence interval are two different things. The confidence level is the percentage and the confidence interval is the actual upper and the lower bounds of the estimate. So given the confidence level in percentage, we know the corresponding z-score. Using that z-score, we can find the confidence interval, the upper and the lower bounds. In this confidence interval formula, if population standard deviation sigma is known, we can use sigma in place of the sample standard deviation s. These are the different formulae which you have to remember, and these are the normal curves with given mean and standard deviations.